Welcome everybody to the UFS webinar. The webinar is hosted by the National Weather Service Office of Science, Technology, and Integration. The goal of this webinar series is to enhance communication and share advancements in all aspects of the UFS in both research and operational settings. My name is Alex, and I'm here to help coordinate and deliver the webinar. Feel free to contact us at OSTI if you have any comments, questions, or suggestions. Also, if you have any recommendations for speakers that you'd like to present at this webinar, you can email your recommendations to ufs.modeling@noaa.gov, and we will take your suggestions into consideration. Due to the high number of attendees, you'll be in listen-only mode during the event. You will not be able to unmute. If you have any questions now or during the event, please submit them in the Google Chat document that will be provided in the chat box shortly. Presentations will each last about 25 minutes, and then we'll have some time after for Q&A. So for this webinar, we'll have two speakers. The first webinar will be by Dr. Jianping Huang, and it will be the UFS AQM online prediction system for enhanced fire predictability. Dr. Jianping Huang recently joined the Environmental Modeling Center at NCEP as a physical scientist. He earned his PhD from Hong Kong University of Science and Technology and completed postdoctoral research at North Carolina State University and Yale University. Currently, Dr. Huang serves as a project lead overseeing the transition of the UFS AQM online system for research to operation AQM v7. For the next steps, he will lead the development of the RRFS AQM online prediction system within the UFS framework, facilitating its transition from research to operation for high-resolution applications. The next speaker will be Dr. Patrick Campbell with ongoing research and developments for NOAA's next generational air quality model. Dr. Patrick Campbell is a research associate professor at George Mason University and a NOAA Air Resources Laboratory affiliate through the Cooperative Institute for Satellite Earth System Studies. He received his PhD from the University of Wyoming and later received a postdoctoral fellowship at North Carolina State University and the US EPA. He is currently the Associate Director of the Satellite and Earth System Studies program at GMU. His area of research is atmospheric composition and air quality modeling, more specifically focusing on air surface exchange processes, including atmosphere-biosphere interactions. He closely works within the chemical modeling and emissions groups at ARL for research and development for the next generation atmospheric composition prediction models at NOAA. So I'm going to turn it over to our first speaker, Jianping.
Good afternoon, everyone. So thanks, Alex, for the. Can you hear me, Alex?
Yes, we can hear you and we can see your screen. Thank you.
Good afternoon, everyone. Thanks, Alex, for the introduction, and thanks STI modeling program for the invitation. I'm very happy to present on behalf of the AQ team at the EMC on our recently modeling development work. This is a joint effort contributed by many people from multiple organizations across the NOAA, including OER labs like ARL, CSL, GSL, TSL, NESTIS, and our university partner. So why do we need air quality forecasting? So as we know, exposure to higher level air pollutant may cause a significant health impact on vulnerable population like children, senior citizens, individuals with pre-existing health condition like lung disease. In the US, the poor air quality can cause over 100 care deaths annually, which is an order of magnitude higher than the total mortality caused by all other phenomena combined. So it's important for us to provide regular and accurate air quality forecast to alert those people to reduce or avoid the exposure to poor air quality. So our customers include the general public, state, local air quality forecast, and other federal agencies. So Wi-Fi is represent one of our most concern for air quality prediction. So Wi-Fi have a significant society impact in terms of CPI adjusted dollars. Wi-Fi is ranked next Hurricane heat wave and jolt. And in the meantime, the Wi-Fi are significant sources for many air pollutants. Over past several decades, the anthropogenic emission keep decreasing. The frequency, the duration, and the intensity of Wi-Fi have been increased. On the right shows the total burning area of Wi-Fi across the corners. So over past 40 years, we are seeing the clear increase the trend. So it's important for us to improve the representation of fire emission and improve our model prediction on the impact on air quality. So NOAA provide air quality forecast through national air quality forecast capability. The initial capability was implemented in 2024 for Northeast US and expanded 2005 for the Eastern US and followed by coverage of counties in 2007 and Hawaii in 2009, Alaska in 2010. So before 2016, we only provided forecast for ozone, and since 2016, we have been provided both the ozone and the PM 2.5 prediction nationwide. To facilitate air quality prediction, we need both the air quality model and the meteorology model. For air quality model, we have been using the CMAG, which is developed by US EPA and maintained by regularly. And for the meta model, actually, we are using NCEP operational forecast model. We used to use a regional model name. Now we are using the GFS model to provide a meta field to drive our air quality model. Until now, so the coupling of the meta or weather with the chemistry model has been based on the offline coupling. So the many operational model actually they are built on with the decibel system. So the UFS system actually aim to unify those previous decibel system into a single framework. So rely on our community for modeling and component development and improvement. So for air quality, actually we have been using the community model as a base for operational air quality and atmosphere composition. We work closely with the US EPA for CMAG and collaborate with NASA for GOCAR for improve the atmosphere composition predictions. So NOAA support more than 20 operational prediction system now leading the effort transition those prediction system to UFS applications. For regional air quality, the AQM actually based on the CMAG driven by GFS meteorology. So eventually, the AQM will be integrated to RFS version 2. The AQM will be part of the shorter range regional UFS applications. For the longer term, so AQM prediction will based on the RFS currently testing at a high resolution of 3 kilometers. So we'll integrate the CMAG into RFS in the online mode. So to address the impact of Wi-Fi on air quality, especially so we'll improve the chemicals speciation and polarized algorithm for fire emission, and we'll using the data simulation to prove the chemical ignition condition. And also we'll develop a machine learning emulator to improve the online air quality prediction system. And this is a highly coordinated NOAA efforts among the EMC, NESTIS, OER labs, and our university partner. So since the RF is still on the development at this point, we are focused on the development of the UFS AQM online system, but with the consistent meteorology, but at a cost resolution of 13 kilometers. So here diagram shows the UFS AQM online coupling the forecast model, which is the center of our prediction system. On the left shows the we are using the UFS-based atmosphere model to provide a meteorology field to drive our air quality model predictions. So air quality model actually is based on the CMAG. Here we treat it as a Korean model because we turn of the transport term, so the CMAC is only used to update the concentration of chemical species at each time step and send back the chemical concentration back to the atmosphere model and allow the dicot to handle the transport for chemical species. So with this online coupling, and both atmosphere model and the air quality model can run on the same model grid and using the same coordinate and same transport algorithm and same physical packaging. So this can avoid a lot of uncertainty related to the grid mapping and the vertical interpolation that's related to the offline coupling. So with this online coupling, and we are supposed to provide more accurate air quality predictions. So this online system has been testing in near real time since July 2022 over a single large North American domain indicated by this red boxes. So which covers the current 3 existing operational domain, Kaunas, Hawaii, and Alaska. So indicated by this blue boxes. So during the neural testing, so we keep integrated any update into our system and include the system into our support our real-time testing. And since the system has been tested at a similar resolution to GFS version 16, so here we propose using the same physical theory of the GFS version 16. So one important feature for this online system, so we are able to integrate the satellite retrieval real-time Wi-Fi product for our fire emission calculation. So I also highlight some of the other important configuration here. I'm not going to talk about detail. So first, now I'm going to present some of the case studies. The first case for the Quebec file. So that's happened in the last June. So on the left shows our online prediction system predicted hourly PM2.5 concentration during this Quebec fire events. So during this event, actually, this storm generated anti-cloud wind bring this plume from the South Canada to US affect the air quality for most states over the eastern US significantly. So actually our online system model captures this event pretty well in terms of the predicted PM2.5 concentration, magnitude, and also the spatial patterns. So here is a snapshot comparison for model predicted PM2.5 concentration. On the left, this is our current operational model predicted hourly PM2.5. So we can see, so current operational model actually significantly underpredicted PM2.5 concentration during the event. If we compare the observation indicated by these circles, filled with colors. On the right is our UFS AQM prediction. We can see we predict a much higher concentration of PM2.5, and which show better agreement with observations. So here the time series comparison between the UFS AQM prediction and the current operational model. We also compare both model prediction with air observation data. So on the left, the red curve represents the online system prediction, and the blue curve is the current operational model, and the black curve is air observation. So we can see our online system actually predicted this peak value very well in terms of the magnitude and timing, and the current operational model actually significantly underpredicted the PM2.5 concentration during this event. On the right is showing the performance diagram, so which includes 3 verification metrics. So on y-axis shows the probability of detection, and x is a success ratio, and those shaded areas represent the CSI critical successful index. So if we compare red curve our AQM online prediction with this blue curve operational system, we can see this online system has higher POD value and higher CSI value compared to the operational model for different threshold value indicate that this online system has better performance in predicting the PM2.5 concentration. And this is a second case for related to Alberta fire in mid of last July. So left showing the operational forecast we can see for this case for Alberta fire case. So actually operational system second over predicted PM2.5. And if you look at on the right, our online system actually improves over prediction and match with the observation better. And also, we are interested in how this online system performs in particular ozone exceeding events. So actually, we observe several ozone exceeding events during this Quebec fire event. And on the left is our operational model predicted daily 8-hour maximum ozone. If we compare the ELNA observation data, actually operational system and significant underpredicted the ozone concentration. And if you look at on the right-hand side, so actually our UFS AQM online system improves this under prediction and can capture this ozone exceeding better over the northeast coastal regions. And so next, so here we just show our online system real-time performance, especially focus on the Wi-Fi events. So next, I'm going to present the more comprehensive evaluation for UFS AQM to support the AQM version 7 implementation. Here we focus on the 3 time period, 2 months for summer and 2 months for winter and 1 month with intensive fire. So here we focus on 2 products. One is the daily 8-hour average maximum ozone, another 24-hour average PM2.5. And this diagram shows the CSI comparison between the AQM version 7, which is based on the UFS AQM, and AQM version 6 is the current operational model. And on the right, this is the red curve represent the AQM version 7 prediction, and the blue curves represent the version 6 represent the operation forecast. So, and in this figures, solid curves represent the model raw forecast, and the dashed curve represent the batch collection. So here we only focus on model raw forecast. So we can see version 7 actually has a higher the CSI value compared to version 6, which means that AQM version 7 has a better performance in particular ozone exceeding event. So here, if you look at this blue lines, as indicated national air quality standard for ozone, so 70 ppb. So any concentration higher than 70 ppb represent the ozone exceeding events. So we can see that AQM version 7 shows a better performance in particular this is the ozone exceeding event in summertime. And this for PM2.5 in summer 2022, we can see for model raw for AQM version 7 has higher CSI value and compared to AQM version 6. So, and 12 microgram per pure represents the annual mean for PM2.5 standard, and 35 microgram represent the daily national air quality standard for daily mean of PM2.5. You can see actually version 7 improves this the 24-hour average PM2.5, especially improves this the PM2.5 exceeding events. And just for the fire season, in September 2020, so we are consistent seeing the version 7 has better performance in particular PM2.5 concentration at a different threshold value, and also for those the 12 and 13 microgram per cubic threshold values. And this table summarizes AQM version 7 verification statistics. So here we compare AQM version 7 with version 6, and for ozone and PM 2.5 prediction over the eastern US and Canada, the upper row and the bottom rows show the comparison for western Canada. So we compare several parameters. So average forecast critical successful in the probability of detection and the false alarm. So if you look at the western US, actually, AQM version 7 shows the improvement for both ozone and PM 2.5. For model law forecast, actually, we did not see any degraded performance except that we've seen some degraded for little bifurcation results. This is for the summer 2022, and for the winter case of months of 2022. So we are seeing for western Canada actually. So we are seeing the improvement for PM 2.5 prediction. We see some of the degraded performance for both the eastern and the western Canada during the winter in terms of the hourly average ozone concentration. So this is some of the challenge, and for the winter time, for night time, is something we like to implement for the next implementation. And for the fire event September 2020, so we are consistently seeing the improvement for by the AQM version 7, and for both ozone and PM 2.5, except some of the slight degrade for model law forecast in over the eastern Canada based on the critical successful index. But one thing we are seeing here is we are seeing this the degraded performance for false alarm. But we know that higher the POD value, most compared with this higher value of for false alarm. So I know the air quality forecast is a concern AOD more than the false alarm. They don't want our model miss any of the event predictions. So summary, so NOAA has developed this online AQM prediction system within this US framework. Actually, this is the first time for us to develop this online system and target operational implementation. So with this online system, we improve the percentage of Wi-Fi emission and improve the impact on air quality prediction. So through this integration of the real-time live data, we are seeing this online system showing the significant improvement for PM 2.5, especially during the fire events and summertime. And we are also seeing some of the better performance, in particular ozone events during the fire event, and compare optional model. So the UFS AQM online system actually has been approved as the candidate to replace the current operational model, and the implementation is planned in the next month. So once the AQM version 7 is implemented, our focus will immediately shift to the development of UFS AQM online system at a high resolution to address the air quality prediction challenge over the complex terrain and the coastal region. And since this air quality meteorology online system is very, very expensive for computation, so we will develop a machine learning emulator to improve the computational efficiency that allowed to run our online system at high resolution. In the meantime, we'll update the CMAC model version along the anthropogenic mission. So I think the patch will present more detail about this one. We'll continue to improve the Wi-Fi emission and performance algorithm. And definitely we are going to use the testing, the data simulation to improve our chemical ignition condition and to further improve the Wi-Fi and air quality prediction. That's all for my presentation. Thanks for your listening.
Thank you so much, Xiangping. I'm going to now switch it over to Patrick for the next presentation.
Okay, hope you can hear me and see my screen.
Yes, we can. Thank you.
Great, thank you so much. Okay, good afternoon. Yeah, thank you, Alex, OSTI, and the broader UF community for the opportunity to discuss here our ongoing research and developments for NOAA's next generation air quality model. Thank you to Jianping too for getting us kicked off with a nice overview presentation of UFS AQM, the system and its improved wildfire predictions and evaluation. As is the case though, this is entirely a team effort. I'm here representing my colleagues at George Mason University, Cooperative Institute for Satellite Earth System Studies, NOAA Air Resources Laboratory and Environmental Modeling Center, Environment Climate Change Canada, and other collaborating agencies not shown here. So for a brief outline, I do have a three-part talk on our current research and developments led at the Chemical Modeling and Emissions Group at NOAA Air Resources Laboratory. And this includes some highlights of the R&D we have to advance the future of UFS AQM, all in different ways as compared to what's being used currently in the AQM as shown by Jianping previously. So first, I will look at and show some of NOAA's UFS AQM component and the major science updates that we're doing. Secondly, I'll talk about moving beyond what is known as the big leaf model in the UFS AQM. And then third, I'll wrap up showing some results on updating the anthropogenic emissions in the UFS AQM. So for part one, you've heard plenty so far on the UFS-based AQM, which is i.e. the new online coupled CMAC component that's being used in the next generation air quality forecast model from Jianping earlier. So I won't repeat that, but here I do show a diagram of a typical chemical transport model where the red boxes highlight the relevant processes that are used in the CTM included in the air quality model component. And we at ARL are working on updating this AQM component, chemical component, or CMAC, the Community Multi-Scale Air Quality Model. However, currently it's a relatively older version 5.2.1. This was released about 7 years ago, and we are moving and developing towards a more state-of-the-science version 5.4, which contains major code and science changes that impact the future forecasts. And overall, there are major structural changes when doing this to the UFS AQM when we update to CMAC 5.4. And I just wanted to highlight some of these developments. We're preparing a paper on this, which goes into detail. But these changes include changes to the emissions handling using the new decide module in CMAC. The newer CMAC uses a centralized I/O structure, and CMAC also uses the ELMO module, or the explicit lumped air quality model, that really simplifies all the CMAC throughput. And all of this is shown on the left and leads to many structural changes that need to happen for this update and development. But maybe more excitingly, it's one more exciting development is the overview of the major scientific changes. And there's a long list of chemical model changes to CMAC since version 5.2.1. And in fact, yes, it was released about 7 years ago. It's gone through two major version changes, the 5.3 and now the State of the Science 5.4. And in the first bullet, there is an updated chemical mechanism to the carbon bond version 6, revision 5. This has major scientific updates to things like photochemistry, including updated halogen chemistry and even DMS, and also the photolysis rates used in CMAC. And then also in bullet 2, there is an updated aerosol module from Aero 6 to Aero 7, and this largely changes the secondary aerosol, organic aerosol formation and inorganic formation considerably in the model. And then there are other updated processes as well, and the major dry deposition and also aerosol dry deposition that impacts our predictions. And overall, all of these changes lead to significant impacts on the predictions of near surface air quality, such as near surface ozone or smog, and also the harmful fine particulate matter concentrations, PM 2.5. So here I show our UFS AQM model configuration with all the gory details on the left of the major model attributes, with some notes of the highlights on the right. So we note again a major update to the UFS AQM here, as presented by John Ping nicely earlier, is that we're using the novel hourly satellite-based RAVE emissions for calculating the fire emissions. This is the Regional Hourly Advanced Baseline Imager, or ABI, blended with VIIRS for the emissions. And we are running over North America, a larger domain by 13 by 13 kilometers with 64 vertical levels, and using a CCPP FP3 GFS version 16 physics. I'll get into more of the other emissions that we are using as inputs and how we're trying to improve them later. But what I will say in red and below, shown in red highlighted here, for everything that I show next, this is going to be a 1-month warm start test simulation for last summer, August 2023. All conditions are held exactly the same, except for our update to CMAC version from 5.2.1, which is using the current AQM, version 7, to now this state of the science CMAC version 5.4, or the AQM, we'll call AQM new, AQM V7 new. And jumping right into some of the results on the left, these are showing results of our major updates to the science, an update to the CMAC and UFS AQM for near surface ozone predictions. And this shows that the average summer evaluation of August 2023 near surface ozone predictions are largely improved. And I show on the top left the spatial overlay and the mean bias plots compared to US EPA Air Now observations at the surface for the current AQM V7, and then below that is the AQM V7 new with the CMAC update, major CMAC updates. And what we see is that we do have this predominant overprediction in red, particularly in the eastern US and southeast US, and we largely improve that when we update the science and CMAC on the bottom right. And also when looking at the CONUS average hourly ozone observations on the top right, and then the maximum daily 8-hour rolling average concentrations for ozone on the bottom right, the updated AQM shown in blue, is in much better agreement with the observations in black compared to the current AQM V7 at both day and night. And again, the maximum daily 8-hour average is a good metric for our peak values in the day and related to the NAAQS standards of ozone exceedances, and our updates to AQM V7 new in blue are in much better agreement with the observations. And so looking at some typical forecast metrics, these are also used in our weather forecasting, of course, but we also use them in air quality forecasting, like hit rate, false alarm rate, and the critical success index, CSI. And CSI, I'll just note, is defined as the ratio of the hits to the sum of the hits, false alarms, and misses, and some of a more representative forecast metric. And I'll just note that first thing we notice here, and the thresholds are on the x-axis for different concentrations. The AQM typically has a harder time predicting the higher ozone concentrations, and these are, again, these are important and pivotal to capturing the poor air quality events that are harmful to the public and ecosystems, et cetera. But what we'll note is that overall, the AQM new in blue is better compared to the current AQM for all the metrics shown here. This is for near surface ozone. And other CONUS-wide statistics below in the table, like bias, correlation, error, and index of agreement, as highlighted in bold, are largely improved over CONUS for our updated AQM V7 new. So that's for CONUS on an average, but what about the different regions across the US or CONUS? And so here we show the impacts of our updated AQM new for near surface ozone again, but this is for different regions with the box whisker plot on the left and an index of agreement scorecard on the right. This is for, again, near surface ozone, and these regions R1 through R10 pertain to US EPA airshed regions shown in the insert image in the top right, if you can make that out. But I just note the AQM new in orange on the left in the box whisker plots performs significantly better than the current AQM in green for ozone in all regions for these different air sheds, as shown by the median in the middle of the boxes, and also the quartile ranges are closer to the air now observations in blue. For the scorecard on the right, each tile here represents a region on the y-axis and then the different data on the x-axis. Where the darker shades red, this means a significant improvement in IOA, or index of agreement, for AQM new versus the current AQM. And what we see is the vast majority of tiles here across regions in different days in August 2023 are red and dark red, showing significant improvements of our updated AQM new. And then jumping to the near surface fine particulate matter, or PM2.5 concentrations, as another typical parameter that our air quality models predict. We do see comparable results with the updated model, particularly in the heavy fire regions of this time period of August 23, in the west and northwest portions of the domain. However, we do note that the updated AQM new is consistently lower than the current AQM, and this could lead to further underpredictions in PM2.5 compared to the current version, especially in the eastern US. And this is likely due to, as I mentioned before, there is a large change in the aerosol dry deposition algorithms, and this enhances aerosol dry deposition loss processes in our updated CMAQ 5.4 and AQM new. But overall, it's comparable results around fires, and that's a good thing. And we're also further investigating using a diagnostic analysis to identify the lower PM2.5 outside of fire regions. However, as for the typical forecast metrics of hit rate, false alarm rate, and CSI, we do see that AQM V7 new here in our updated model improves hit rate and false alarm rate, very similar critical success rate index. But we largely do improve those forecast metrics. And there's sort of a mixed in terms of improvements or minimal changes to some degradation in the overall statistics in CONUS in the table below. But looking regionally again, on average, the box whisker plots on the left do show that our AQM V7 new in orange agrees better, really better actually with our observations for nearly all regions compared to the current AQM V7 in green, compared to the blue US EPA Air Now observations. But as indicated by the daily IOA scorecard on the right for each region, there are certainly areas in later August in the eastern and northeastern regions of the US that had some degradation. As I mentioned, there likely is almost too strong or too strong dry deposition loss for the aerosol and these updates, and we're investigating that further for the developments. Okay, so pivoting to part 2 of my talk, I'll talk a little bit about our project on moving beyond what's known as the big leaf model in the UFS AQM. And so typically and historically, a big leaf approach is used in our numerical weather prediction models and air quality models, where the big leaf approach is used to represent the plant canopies of the surface as a homogeneous single layer without any real vertical structure. I showed it in a diagram on the left here, where multi-canopy layers in the diagram shown on the right are more costly as they represent the fluxes and conductances within each level of the canopy, or however it is defined, but it can really represent the vertical variability of this canopy's physical and dynamical and chemical traits. But the problem is application of these multi-layer approaches to already costly air quality forecast models with complex chemistry at such large regional scales, like in our UFS AQM, presents some further challenges. So what are we doing to overcome this? Well, in this project, we note that first, the top bullet here, systematic ozone overpredictions in chemical transport models like CMAQ or the AQM, these have been linked to distinct gradients of ozone within dense forest canopies in the US, which are darker and have less turbulence, or modified turbulence, I should say. And so what we're doing here is we're bringing in 2 parameterizations, one for the parameterization of the associated photolysis attenuation, or the attenuation of light in the darker forest canopy. And also, we're bringing in canopy vertical diffusivity modifications or turbulence modifications within a canopy. And I show here a typical surface ozone bias, as you saw previously, where they have these typical over-predictions, most predominant and strong in the eastern and southeast US in regions of contiguous canopies. So we're bringing in these parameterizations that are computationally efficient right now to address this issue. And this is based on collaboration with Paul McCarr and Environment Climate Change Canada. We are also developing a high-resolution 1 kilometer global canopy data sets to use with these canopy parameterizations and within the UFS AQM. And this is based on a suite of satellite data, including MODIS, VIIRS, and JEDI. And these include parameters like leaf area index, the forest fraction, the forest or the canopy clumping index, and the canopy heights, forest canopy heights. And we're doing this for direct inputs into the UFS and UFS AQM, but also for our novel development of what is known as the Canopy app, which is an explicit but efficient standalone canopy model that we're developing for research and application to the UFS atmospheric composition applications. So these data sets are being developed for both standalone research and future integration into UFS and their applications. So here are some preliminary results of the impacts of these vegetative canopy effects on ozone, surface ozone predictions. And this is an average hourly ozone simulation for August 1st to the 15th, 2023 in model layer 1. And we have the base concentrations on the left without canopy, and then on the right we have the difference plots for including the canopy minus no canopy. And the impacts of this reduced photolysis or darker forests and shading in the modified diffusivities or turbulence leads to widespread and in some cases large ozone decreases daytime and nighttime at the top and the bottom, snapshot here in time. And in some cases, relatively large ozone decreases in the densest forest canopies of up to 20%, or 5 ppb in the current implementation. And then evaluating this impact here shows improved model performance. The base on the top left, this is again the spatial bias plot for the simulation minus the US EPA air now observations at the surface, and the canopy on at the bottom. It reduces the overpredictions in the regions of contiguous canopies. A little difficult to make out here, just comparing these two. But it does reduce the bias and reduce the error and improve the index of agreement slightly here compared to US EPA air now. And on the right, looking at only the eastern US region, like mid-Atlantic. But here I show the diurnal pattern of surface NO2, nitrogen dioxide concentrations, and ozone at the bottom. And there is an increase in NO2 slightly and for the canopy model, and a reduction in ozone, which are a better agreement with the observations. And I'll just note that, yes, it may not look somewhat small impacts right now. We have to take some caveats when comparing against the US EPA or now observations, but we're also working on a revised version of the canopy codes for a more explicit layering approach. And this will increase the canopy effects and will ultimately move the ozone over predictions closer better to the observations, particularly in the forested regions. And now finally, I'd like to wrap up with the third section, pivoting to our updates to the anthropogenic emissions in the UFS AQM. Sorry, I'm having a little trouble advancing my screen. So I will say that emission inputs to an air quality model or any chemical transport model are arguably the most critical input. And so currently, for the UFS AQM system, we use what is known as our Nexus model, which is the NOAA emissions and exchange unified system, to generate and seamlessly combine regional and global area source emissions from anthropogenic sources. So the Nexus model is built upon Harvard's HEMCO emissions model, which is also used in GeoSchem in the global community model, global chemistry community model. We have a figure, a diagram on the top right in the paper showing the proposed implementation of Nexus within the UFS. But I will just say that here we use Nexus in our UFS AQM to blend together a suite of global and regional emissions that include currently, for the current version of AQM, SEDS version 2, from the year 2019. This is for all gas emissions, SO2 over the ocean only though, and organic carbon and black carbon globally. We use the OMI HTAP sort of fused top-down, bottom-up method for SO2 emissions from 2019 for land only. And then we use the HTAP version 2 from year 2010 for primary coarse and fine particulate matter. And then we use the NEI 2016 version 1 modeling platform for all gases and aerosol emissions inside CONUS domain only, as it's only provided in that region. But the issues here are in red below, where the current versions of NEI 2016 and HTAP version 2 from 2010 are relatively outdated for air quality forecasting. And also, I didn't mention, but all these global emission inventories that we're blending in here are monthly static emissions in time. They don't have any diurnal, daily or diurnal patterns. So one major update we're working on is to use a high-resolution regional 1 kilometer emission data set. And this is based on the Neighborhood Emission Mapping Operation, or NEMO emissions, developed at George Mason University with our collaborators Siqi Ma and Daniel Tong. And it's based on a synthesis, really, of a number of different spatial surrogates, shown on the left, including geographical information, geographical information including population, roadways and traffic, and things like railroads. And then without going into all the details, we have this middle flow chart here, detailed flow chart, and how this data set is developed using these spatial surrogates and then also the speciation and temporal allocations, all coming together to update our emission inventory also from the 2016 platform to 2019. Where the animation on the right shows impacts going from a 1/4 degree global inventory to a 0.1 degree global inventory, or our current blended regional inventory, which is like what's used in the current UFS AQM, down to the high resolution 1 kilometer NEMO emissions. And you'll notice that the high resolution NEMO emissions capture much more granularity in this area of like the New York, Long Island Sound region, and will certainly impact the overall UFS AQM predictions of surface ozone and PM 2.5. And so just showing a quick example impact of the updated nitric oxide emissions, comparing the new NEMO NEI 2019 emissions from GMU compared to what we currently use. What we currently use in the top left is here, and below that is the difference between the NEMO 2019 emissions and our current. And what we see, as anticipated, there are widespread decreases in the emissions covering this area of CONUS due to these, not just the year update, but also the higher granularity and the higher resolution emissions. And this is agreeing, and I'll just also note that this is leading to about an average 40% decrease in nitric oxide emissions over CONUS. And this is agreeing largely with decreasing trends in NOx emissions since 2002, as shown here in the US EPA equates data set. And I don't have time to go into all the details of what we're updating here. There's a lot, but the full emission updates actually include more. It includes more recent regional and global inventories, but also the use of what's known as the CAMS tempo from collaborating with the European colleagues. And this adds the needed and the really necessary temporal profiles for global gas and PM emissions in the regions outside the domain, outside the CONUS domain portion that come from the global inventories. So really, in summary, the emission updates that we include the update of the regional NEI 2016 version 1 to the GMU NEMO high resolution NEI 2019, that's inside of CONUS only. We update HTAP version 2, 2010, to the HTAP version 3, 2018 for the primary PM emissions, that's outside of CONUS. And also we're using CAMS tempo to fix this issue of having no diurnal or daily temporal profiles for the major gas emissions from the global inventories. And so we apply these CAMS tempo grid weights outside of CONUS. And what it leads to, showing NO2 emission differences and SO2 emission differences here with the animation, we see that has large impacts on these emissions, and this will translate to large impacts of future UFS AQMs ozone and fine particulate matter. And we'll be testing these in the future. I also just will briefly mention, as I'm running out of time, we're including some other developments as well for the anthropogenic emissions, including weather-dependent emissions. For example, mobile emissions from the on-road and off-road networks are indeed sensitive to things like temperature and humidity due to various factors. And we are not currently including that in the UFS AQM, but a future development will bring this in and test that. And this could lead to large impacts on ozone locally, as shown here for San Jose, California, but without the temporal or weather-dependent effects, and then the difference for ozone near the surface, and they're significant. And finally, our Nexus emission model used in the UFS is being further developed, and I'll mention some of these developments here, to become its own UOPC component in the UFS. Initial UOPC driver for standalone Nexus has been created, and this is being tested currently using a data atmosphere. And we're testing that to use Nexus for process-based dynamic emissions as well, for like biogenic emissions, windblown dust, sea salt, etc. And then the two-way coupling will be tested next for the UFS AQM. And we're also developing new capabilities for the advanced Nexus, including alternate biogenic emission options from development of newer versions of Megan for the biogenic emissions, or even to use our Canopy app, as I mentioned before, for generating leaf scale biogenic emissions. And the animation shown here on the right just shows Nexus and it's provided diurnal pattern of primary PM 2.5 emissions, which is pretty interesting. It almost correlates very well with sort of city lights. It looks like city lights almost near the urban centers, but just showing the capabilities of Nexus in the UFS. And then I'll just wrap up here. So the progress and the future of the UFS AQM, we at NOAA Aero are really going to continue and further evaluate CMAQ 5.4 and the updates to the AQM new version. And we want to do more testing and a hopeful future transition. One thing we also want to do is update and improve the diagnostic capabilities in the UFS AQM, such as outputting fluxes, dry deposition rates, chemical process analysis, etc. This will help us better understand the AQM scientifically so we can better develop it. We're working on a comprehensive evaluation paper now. As I mentioned, moving beyond the big leaf model, we want to update the vegetative and canopy codes and the data sources from satellite and evaluate the impacts on its near surface ozone predictions. And finally, want to continue advancement of Nexus and its integration of updated emissions, and then thoroughly test that and evaluate the impacts of the future of UFS AQM predictions. And that's all. Thank you so much. Sorry, I went a little over.
Thanks, Patrick. I'm going to change over the screen now to our question and answer document, and let's start answering questions. Are you able to see that screen? It looks like we've got one question on here right now. What are the major differences between AQM version 6 and AQM version 7?
Yeah, I can see the question. So I think in terms of the difference between AQM version 7 and AQM version 6, actually, version 7 is totally different from version 6, even the number just updated, not simply just updated. Well, version 7 the simple update from version 6. So version 7 actually is the online coupling system, and version 6 is the offline coupling system. So that's one major difference between two models. The second difference for this is the implementation, it's the Wi-Fi emission. So for version 6, they're using the GBB-EPX, which is a daily mean, and normally the real-time testing, the operational real-time, they use 1 day old data. But version 7, so we are using latest satellite travel data, lift data. That's hourly emission data and the high resolution, and no 1 day delay. We can use the real-time data. That's regarding the fine emission. The third difference between two models is about the model domain. So the version 6 actually for operational, we run the system 3 times, one for Canada, another for Alaska, and the third one for Hawaii. So that's very difficult for us to maintain the system, run the system for 3 times. This time for version 7, we just need to run one single larger domain. So all the product for 3 operation domain just generated based on the one single domain predictions. I think that's the 3 major differences. Thank you. This is a question for who? For me or for Patrick? I think let me answer first. So I think for AQM version 7, so like I said, the major contributor for this improvement, first is the model coupling way. So the version 6 actually they're using the offline coupling, so which means we provide a meta input at the interval of hourly. Actually, version 7, since both the meta model and the chemistry model are linked dynamically, so that we can update the meteorology field at each integration time step. So we suppose that the more frequent meta field ingestion support will provide a better air quality prediction. That's one key reason cause this contributes to a significant improvement. The second, like I said, this is the Wi-Fi emission. So now version 7 using the real-time hourly data. So compare version 7, they're using daily mean and 1 day old data. That's another big improvement. No, so even the AQM version 7, we're using the online coupling, so we can send the aerosol all the chemicals back to the atmosphere model. But at this moment, we did not include this aerosol feedback on the meteorological field. So version 6, that's offline, so no any impact. But version 7 has the potential for us future using this as a real-time update aerosol to investigate aerosol feedback on the metal field. That's the reason why we move this online system. So this not only benefit our air quality prediction, but potentially will benefit the metal field prediction in the future through this also the feedback. So regarding the plume rise impact in AQM version 7, yes, we have done a lot of testing during the model development stages. For instance, so we try to, sometimes we are seeing some like the case we testing for the Wi-Fi in September 2020, that file located northeast coastal region. So that file we are seeing sometimes we are seeing the significant under prediction. So because this time for AQM version 7, the fire emission distributed vertically. Right now I follow the linear decrease the relation. So we did not. So there's something we did some testing. Like for instance, we put 80% of the fire emission on the plume rise side, and also we try to put a different ratio. So how can distribute this is the fire emission vertically. So but we haven't put any data we've seen. But finally, because we need to verify our version 7 prediction for both PM 2.5 and the ozone prediction. So in this AQM version 7 implementation, so we decided using follow this linear decrease in the distribution pattern. But this is something we still want to improve for the next implementation. For example, so we made some significant on the publication for this text file in February this year. So that's something, because that's related to the glassland file, not the forest file. Maybe the polymerize, but polymerize is calculated based on the FRP. So maybe that's not the bad way, a good way for predict this is the file event for the glassland file, even for agriculture file. This is something we want to implement for next implementation or future implementation.
All right, and it looks like we're getting that time. It looks like we just have 2 more questions. Patrick and Jianping, do you have time to answer those real quick before we sign off?
Yeah,
Okay,
I mean, I barely see the question down there, but I think Jianping already kind of answered that, right? I think the AQM development is primed for and ready for, testing these air quality weather feedbacks, or like the direct and indirect effects. The capability is there. It needs to be developed and tested, and its impacts on weather.
Okay, for the last question regarding this scavenging, so for AQM7, so all the chemical species, like I said, we pass this chemical species concentration back to the atmosphere model, so allow the dicot to deal with this transport. And also we are using the same scavenging, this wet scavenging scheme, the algorithm for chemical species. So that's the same for also the other tracer used by UFS for both for aerosol and for gas species. We're using the same convective weather scavenging. And I'm not sure that is similar to the SAS scheme, but I know that we are using the same convection or the other trace used by the default trace used by UFS model. That's the same algorithm used for chemical species for both aerosol and for chemical for gas species. But another larger scale scavenging that is still handled by CMAG itself. So this is a convex wet scavenging handled by DICOM with the same scheme as the other tracer used by UFS. I'm not sure about the other. Probably I need to double check whether using the SA scheme or not. Thank you. I hope I answered most of our questions. If any more questions, send me an email.
All right, thank you both, Jianping and Patrick. Thank you everyone for attending the webinar. Have a good day.
Thank you, Alex.
Thank you. Bye-bye.